A premium chocolate bar is defined by its physical precision. To the consumer, that means a high-gloss finish, a sharp, clean snap, and a texture that melts at exactly 93 degrees Fahrenheit. But the origins of that uniform product are messy and biological. Deep in a tropical rainforest, a farmer uses a sharp blade to separate a heavy, colorful pod from the trunk of a cacao tree. When split open, the pod reveals dozens of seeds buried inside a sticky, wet, white pulp. At this stage, it looks more like a tropical fruit than the raw material for a confection. The central challenge of this material is that these raw seeds possess no chocolate flavor. They are pale, intensely bitter, and lack any of the deep, roasted aroma associated with the finished product. Getting from this sticky fruit to a tempered bar requires solving a massive two-part engineering problem. First, using chemistry to create flavor, and second, using physical refinement to build texture. Flavor development begins immediately on the jungle floor. Farmers pile the wet beans into wooden boxes or cover them with banana leaves to trigger fermentation. Natural microbes begin consuming the sugars in the white pulp, generating intense heat and releasing new chemical compounds. This heat triggers internal reactions that create the foundation of chocolate flavor. Without this step, the seeds remain bitter and flavorless. Once fermentation is complete, the beans are spread under the sun to dry. This lowers the moisture content to roughly 7%, which stops the chemical reactions and prevents spoilage during shipping. The dried beans are packed into heavy burlap sacks and transported by the thousands of tons to high-tech manufacturing facilities. At the factory, the beans undergo a final thermal transformation, industrial roasting. These machines use controlled thermodynamics to remove any remaining moisture and finalize the beans' deep, complex aroma. Chocolate flavor is not an inherent property of the cacao seed. It is synthesized through this coordinated sequence of fermentation and heat. With the flavor established, the engineering focus shifts to texture. This starts with crocking the roasted beans and winnowing away the papery outer shells to isolate the dense inner nibs. These nibs are solid and crumbly. To transform them into a liquid, they are fed into heavy mechanical grinders. Intense friction during the grinding process triggers a phase change. It melts the natural cocoa butter, turning dry solids into a fluid called chocolate liquor. Sugar and milk are added at this stage, but the mixture is still unrefined. On a microscopic level, it is a gritty suspension of jagged particles and harsh acidic compounds. Simply turning the nibs into a liquid isn't enough. The fluid requires extreme physical refinement to become palatable. To fix the texture, the liquid enters a mandatory mechanical process called conching. Heavy rollers continuously knead and aerate the liquid chocolate for hours or even days, keeping it in constant motion. This microscopic cross-section shows the effect of that motion. Physical friction grinds down the jagged microscopic particles into smooth spheres, while constant aeration allows unwanted acidic gases to evaporate. Conching is the physical bridge between a gritty industrial paste and a velvety, premium-quality liquid. The final and most volatile hurdle is tempering, the process that gives chocolate its structural integrity. If liquid chocolate is simply allowed to cool, the cocoa butter fat crystals form in a disorganized way. The result is a bar that looks dull, crumbles easily, and eventually develops a white, chalky coating. Tempering prevents this through a strict thermodynamic loop. By heating, cooling, and reheating the liquid to precise temperatures, manufacturers force the fat crystals into a stable, uniform structure. The clean snap of a finished bar is the physical evidence of this perfectly engineered crystal matrix. The tempered liquid is poured into molds and passed through cooling tunnels, where it completes its final physical state change back into a solid. Millions of identical bars move down the assembly line, each one showing the exact same dimensions and glossy finish. It is a striking contrast to where this journey began, with a sticky fruit hacked from a tree in a tropical forest. The next time you break a piece of chocolate, you are experiencing the result of nature's biology, refined by industrial physics.